Hi, my name is Brad Carman, and this is modeling a hydraulic crash simulation system with Julia. In this presentation, I'll first explain what crash simulation is, and then I'll give a quick overview of why a model is needed, the history of the model evolution, and what led me to Julia. Finally, I'll discuss some details around how I used ModelingToolkit, which, by the way, is the tool I found key to modeling in Julia. How I overcame some technical challenges, including some techniques that can be used to get some big efficiency gains with ModelingToolkit. And in the end, I'll show the successes that I had. So first, let me explain crash simulation. On the left, I have a diagram of what is called a barrier crash, which is what we typically see in commercials. This type of test is expensive because it requires a one-off prototype, which can only be used once because in the end the prototype is destroyed. Typically the vehicle would be fully decked out with lots of sensors and high-speed video to record exactly what occurred. And therefore any issues that are identified, such as a bad airbag deployment, can be recreated in simulation. So on the right we have a diagram of the recreated crash using a sled-based crash simulation system. It may seem a little weird at first because the crash appears in reverse, but from the occupant's point of view, the forces are exactly the same. In this way, a sled can be used and loaded with only a partial vehicle. Sometimes only a seat is required, as shown in the previous slide. Therefore, the test cost is greatly reduced, and it can be repeated exactly to allow design iteration of a component, such as the bad airbag, for example. I have here a diagram of our system. The system starts in the back with an accumulator for high pressure energy storage. The energy is then precisely released and metered through the very large main spool valve. And here is a picture of me standing next to one. As you can see, it's nearly as big as I am. The hydraulic energy then acts on the main actuator, which in turn accelerates the sled. The main valve is controlled with a smaller spool valve, which is then controlled by yet an even smaller pilot valve or servo valve. Therefore, we have a cascaded valve system, and that's controlled by a cascaded control loop. And as you can see, one important point is that the acceleration or force sensor on the sled is not an output which comes back to our controller, and that is exactly why we need a system model, as I'll explain in the next slide. So here we show where the model is applied. First, the model can be used in our simulation or prediction software. Here one can determine exactly how much payload can be applied to the system, for example, as well as making any other edits to ensure that the test will be successful when run on the system, which otherwise may have resulted in a failed test and a costly waste of time. Once the test is prepared, it can be brought to the system where the inverse form of the model is used to calculate a hydraulic command that hopefully properly operates the hydraulics to give the desired output forces. The inverse model has some removed nonlinearities and discontinuities, therefore it's not as accurate. We can improve the calculation by running iterations where a forward version of the model is now used, which includes the full complexity and is much more accurate. So with an outer loop or offline iteration learning loop, we have an improved command signal calculation. So in the end, what is achieved is a much more accurate hydraulic command signal and a reduction of what had previously been done with the physical system, which again is a costly use of time to iterate using the actual system rather than the model. So as can be seen, the model is key to efficient operation of the system, but additionally, the model is also key for uses in engineering design and analysis. So over the last 20 plus years, the model has evolved quite a bit. In the beginning, a simple chain of transfer functions was used for the inverse model, which was of course not very accurate. So when I joined in 2014, the model was expanded with a flat equation-based approach with the goal of eliminating assumptions and increasing complexity. This approach was done in pure code, which worked well and offered some advantages, but it was pretty slow for development and engineering design work. So Simscape was then attempted to provide an acausal type modeling framework as we moved to a higher rate controller, and we hope to increase the model rate as well. So this worked well, but it required a lot of workarounds, and the biggest challenge, of course, coming from the dual language problem. And this is essentially what motivated me to move to Julia. So with the pandemic and things slowing down a bit, I decided to take the plunge and just make the move to Julia. But this required two key technologies that I had to find. First, I had to figure out a way to embed Julia in C#, which is what we use to develop our applications. I was successfully able to achieve this after some study and development of a couple tools, which I'll try to cover in a future talk maybe. And two, what I'll be covering here, I needed to find a way to develop acausal models like I did in Simscape, and I was very happy to find the solution with ModelingToolkit.jl from the SciML organization. So now we can take a deep dive into the technical details of building the model. What I'll describe first is my package, which I call ModelingToolkit.components.jl, which is simply a wrapper package to simply provide some additional functionality to Modeling Toolkit. At the moment, this package is now public. Instead of publishing, I hope to potentially see these concepts eventually integrated into ModelingToolkit.jl, which I'm actively trying to influence at the moment. As can be seen in the list, the topics I'll cover are parameter management, global and parent parameters, derivatives of algebraic variables, and static model code generation, all of which I'm going to now demonstrate with an example using hydraulic modeling. So to start, we need to set up a couple nodes, hydraulic and translational. I'll be showing how this is done with Modeling Toolkit on the left here and using my wrapper package on the right. Under the hood, the same code is called using the at variables, which I have here, and at parameters to set up the hydraulic node with pressure and mass flow and an initial pressure parameter P int. So similarly, the same thing is done with the translational node. So there's nothing too important happening here, just need to establish the base. So now that we have our node set up, we can define a volume component. So on the right, I have a diagram to define the component, which should be thought of as a cylinder with a mass flow port and a movable wall or cap. So the translational port. Therefore, this can be used as a building block for an actuator, for example. There are a few parameters we need to define here for the geometry and the hydraulics. I'd like to define the components so the initial pressure can be set, so we have a P that comes in and that flows down to both of our nodes and to our pressure parameter and our pressure variable. I'll explain in the next slide how this is key for a parent-child parameter relationship. Additionally, the fluid properties should be set to global parameters so that we don't need to define them with each component. So this is shown here, how this is achieved in my wrapper package. Other acausal modeling systems define domains for properties associated with the respective nodes. So if you have a gas node or a fluid node, they'll have parameters that live in that namespace. But for now, I'm just defining hydraulic oil and global is fine. So you can see I'm also defining a time step parameter, dt. I'll explain this in a later slide, but this too should be a global parameter. As can be seen when generating the volume component using Modeling Toolkit, in the way that I've written the code here, I run into a problem. The namespacing gets messed up and the hydraulic node ends up referring to itself. So you can see here h.pint defaults to h.pint. So that's a problem. So therefore we're forced to define the initial pressure by value only, which loses its key parent-child relationship. So we're forced to say p is equal to p the value rather than p equals p int the parameter. On the right, it can be seen that this is exactly what's fixed with my Modeling Toolkit components wrapper package, which automatically adds the additional code under the hood to fix the namespacing issue. So you can see here now we get h.pint defaults to pint, the parent parameter of the component. Additionally, one feature to point out is the pretty printing of the model, which shows the child components and the respective parent, the respective parameters, globals showing here in red and locals showing beside that. So to demonstrate some additional concepts, I'm going to just assemble two volumes together, which would be similar to an actuator, but in this case, it's just a silly example of one volume connected to another volume with forced mass flow and forced translation of the walls. So when generating this system in Modeling Toolkit, all is well because correct initial pressure and forces can be set by value, as we show here. But if we want to preserve the model and only adjust the parameters, which is the case when running a parameter optimization, for example, the code needed is quite tedious. We need to be careful to correctly set all relevant parameters in many places, as I'm showing here, the initial pressure and initial density set in many places, rather than it'd be best if we could just set it with one value. So this problem is solved in Modeling Toolkit components by generating a parameter structure, which I have here. When calling the initialize function, we get a run model object which contains helper functions, u0 and p, which can set the initial values and parameters from the parameter structure. So we also get the simplified system and the ODE problem. So as you can see here, we're able to remake the problem with new initial values and parameters in one line of code by feeding the parameter structure. So let's now take a deeper dive into this volume component. The key to this component is simply defining the conservation of mass equation, which we can see here on line 56. The mass flow in and out of a volume, so .dm, is equal to the change in density and volume. So we have d rho times v plus rho times dv. Volume and density are algebraic terms based on the variables position x and pressure. Therefore, we require derivatives of these algebraic relationships. We can manually define these equations. In this case, they're straightforward, so we just define them here with just some symbolic terms. And so on the left, the way we define this with pre-computed derivatives is we'll call the analytic volume component. On the right, we can take a different approach, allowing Modeling Toolkit to do the work of generating the derivatives for volume and density for us. We can call this the computational component. So you can see here we have the differential operator on density and volume. And our volume and density relationships are brought in as equations now. So we'll call this the computational approach. I'll show in the following slides how this makes a pretty significant difference when calling structurally simplify to simplify our system. One additional key discovery that I made related to model simplification is what I call the algebraic equation hack. What I'm showing here in this first column is the details of solving a differential algebraic equation, a DAE form problem. So we have a mass matrix and the residual and the Jacobian forms of the system, which are used in the Newton iterations to solve u sub I for each time step. If we replace the differential with an algebraic equation using backwards differencing to calculate the derivative, then we convert our model to purely algebraic form, and we're just solving now a system set of algebraic equations. I leave the mass matrix term here, but this actually would go away because we've replaced our differentials here. But as you can see, the residual and Jacobian are essentially the same. And we're solving then the same set of equations, just in a different way. The consequence of doing this is that the time step is now a parameter that is owned by the model. So that's why I have dt highlighted in red here. And this means the model cannot use time splitting or adaptive type solvers. We're going to be doing discrete math here, essentially. But the advantage is the model can be reduced further in this form. So if we now compare this simple example using the computational versus analytic methods, definitions for the volume component, and the DAE versus AE forms of the system, as can be seen, we get down to simply just 4 equations in 4 states using the analytic and AE forms. If we had stuck with the DAE form using the computational definition for the volume, which could have very easily been assumed was the right way to go, is kind of the default way that one would define all this stuff, we can see that this would have ended up being 3 times as complex. So when considering an even more complex model than this just simple model, of course this affects compounds. And that's exactly what I'll show on the next slide with my full system model. What we can see when looking at the full system model, starting with nearly 100 equations and states, is that the DAE form of the model now fails to simplify. I showed 2 forms of the model, a forward version where the valve position is the input, and an inverse form where the acceleration is the input. Both of which are derived from the same base system components. I only adjust which variable is the driving input. This is, of course, a great example of the power of acausal modeling and being able to generate models in pure Julia code. As can be seen, I only adjust one line of code here in both of these systems. And of course, I could make this even simpler. If I had simply used an if-then switch, I could combine these functions into one, which again, this is why being able to model in pure Julia code is so good. But as you can see, in both cases, structurally simplify fails and doesn't simplify the model nearly as much as the algebraic equation type, which is able to provide nearly an order of magnitude reduction from the original system. One final efficiency boost was discovered. I have a requirement to serialize the ODE system for our distributed software. It needs to be delivered in a compiled form. Or in simple terms, we would like to preserve the model simplification step because this should only need to be done once. Modeling Toolkit does give the ability to write ODE systems to file, but we run into an issue when it's a simplified ODE system, which contains what are called observables from the reduced equations. This part is missing essentially because observables at this point are only defined in memory. So step one to serializing the ODE system, we need to include the observables in this serialized ODE system, which I do as shown here with this included code. So then we need to serialize the observables themselves. I did this by applying the build explicit observed function and then doing a string manipulation to the function's signature. So here I'm calling build explicit observed function, and then I do a string manipulation. By doing this, I'm able to include two types to dispatch with, the model name and the observable name. Now I can use Julia's multiple dispatch to call getObserved to get the observables, and now this works with a serialized ODE system. And as I'll show in the next slide, this offers some significant efficiency gains. So putting everything together, we can see the final model performance. I show on this plot several model variations from less complex to more complex versus the model runtime normalized to real time running at 10 kilohertz. So 1.0 would be a model running at real time. And I'm very happy to report that I am achieving my goal for the most part. Open circles are showing the model runtime, and solid circles are including the time to calculate the observables. I show here on the left the difference between the serialized and non-serialized versions of the model. So if we haven't serialized the model and we're generating it from the original, if we're building the model from scratch, then it takes significant time to run structural simplify and put together the ODE problem. Running the model is very fast, but then getting observables takes a significant amount of time. And I can't explain exactly why that is. It seems as if Julia having the functions in memory means that Julia needs to potentially recompile them. And I should note this code has already been pre-run in my active sessions at Julia, so everything here has had the opportunity to pre-compile. Running this serialized version of the model, of course, only takes a fraction of a second to grab the model because it's already been serialized to memory or to code. Running the model takes about the same amount of time. And then most significantly, getting the observables using the serialized dispatchable get observable function has a more than order of magnitude reduction of time there. So that concludes the story of how I transferred my model to Modeling Toolkit in pure Julia. I hope you found this informative and useful. Big thanks to the SciML organization for their great work and tools. I definitely welcome any feedback and questions. There's still a lot more to cover for a potential future talk, namely the second half of the story where I integrate the model into our software. But for now, that's all I have time for, and thank you for watching.